Hi guys, in this video I want to talk to you about Kirchhoff's laws. They're rules that are experimentally verifiable that we use to analyze simple and complex circuits. This definitely comes up in electrical engineering and it's kind of the foundation of analyzing circuits. So let's get started. So this right here is a simple circuit. It's a battery connected to a light bulb. I've labeled the points A, B, C, and D. And what I want you to think about is if you were to measure the voltage typically is the difference between 2 points. So if I basically assume the voltage at A is 0 and think about how the voltage changes as I go across or around the loop, what do you think that's going to look like? So if I start at 0 at A, what do you think the voltage at B will be? At C, at D, and then at A. Predict it. What do you think? We're going to go into the FET simulation, and I'm going to use the voltmeter to actually measure this. So I'm going to put the negative end, the black end of the voltmeter down here by the negative end of the battery. And what the voltmeter does is it takes red minus black. And a battery, this is the high voltage end and this is the low voltage end. So that 9 volts, what does it correspond to? It says like when I take this end minus this end, I'm going to get 9 volts. And that's what the voltmeter reads out. So A is at 0, B is at 9 volts. So looking something like this. Now, what is going to happen in the rest of the loop? It's going to increase or decrease or stay the same. And I want to account for just a little bit of wire resistivity. And when you say that the wires are just a tad bit of resistance, you see that the voltmeter changes as you go across. It's small, but there's something. When I go to the other side of the light bulb, there's a huge drop. And then as I work my way around, back to 0. So 0, 9, very, very small drop across the wire. Big drop across the light bulb, going from 8.98 to 0.06. So almost 9 volt drop. And then as I work my way back down, back to 0. So the shape looks something like this. Just a very small negligible drop almost between B and C. Huge drop from C to D across the light bulb. And then small drop from A back to A. So what we're trying to do is really develop a pattern, because Kirchhoff's first law is really just kind of a generalized pattern. And just based on what we saw for the first one, what do you think it will look like for this loop? As I go around and measure the voltage change from A, B, C, D, F, all the way back down to A, what do you think it's going to look like? Take a second to predict it. And we're going to go and measure it. Negative end at the negative end of the battery, positive end, 9 volts again. Sounds good, nothing too unexpected there. Small drop across the wire. Big drop across the light bulb, not down to 0, or down also 4.5 volts. Small drop across the wire, and now there's another big drop, almost another 4.5 volts. That is 4.47-ish. And this right here was about 4.46. So in both cases, it's about a 4.5 volt drop. So do you see what the pattern is? And when I get back to A, when I trace out this, it looks something like this. Big drop from big increase of voltage from A to B. Small, almost negligible drop from B to C. C to D, there's a big drop, about 4.5 volts. D to E, not much. E to F, big drop. And then F down to A, I'm back down to 0. So do you see the shape? Can you figure out what's going on? One more circuit to analyze. What do you think is the voltage around the loop is going to look like? when I go around this loop, and then when I go around this loop. Predict it. And we're going to go and measure it. So voltage here, 9 volts, cool. Small drop, small drop, small drop, small drop. 8.9 and almost a 9-volt drop across this one light bulb. That's interesting. And then down back to 0. And if I do the same thing for the other one, small drop around the wire, 8.86, and on the other side of it, 0.15. So there's a 8.6 difference, so basically close to 9 volts. And then as I go around, back down to 0. So what's the shape of that? When I go around this loop, big drop from C to D, small drop around the wires. And then for the bottom loop, looks exactly the same. So what's the general pattern here? Do you see what the general pattern here is? I summarized it over here. Sorry, I meant to go bit by bit. But as you go around in a loop, if I start at A and I go around in a loop, I'm ending up at A. So the total voltage difference between A and A should be 0. I should end up where I started. So the total change in voltage should be 0. And that's what we call the loop rule. When I go in a loop, the total change in voltage is 0. And another way of looking at that is like if you brought a charge from here, say a positive charge or proton from here, and I brought it in a loop and I brought it back to this point, electric potential energy only depends on your initial and final position. So if my initial and final position are at the same point, there's no change. Kind of like if for gravity, if I bring this all around the world and I bring it back to that same endpoint, the total change in potential energy is 0 in that case as well. The other small thing is wires have a small resistance, and so we approximate it as having 0 resistance and basically 0 change in voltage across them. We're going to say all of the voltage drop across the circuit. None of it happens across the wire. That's the main point. This we call Kirchoff's loop rule. Hope that was helpful. Take care.